cry.
Okay. Today's lesson has two parts to it. One part is mainly notation, a little bit of theory, and then the second part is all practical application. The practical application is really simple. Okay, it's just geometry. So before we get started, can you find the area of a triangle?
Yes.
Can you find the area of a circle?
Yes.
Can you find the area of a trapezoid?
Yes. Yes.
You might need a little refresher, but you can do it, right?
1 half B1 plus B2 times H.
Close enough. If you can do those three things, you can do the calculus tonight, because that's all we're going to be doing. But we have to talk about the notation and the theory behind that. So we're going to talk about something called the Riemann sum, and then we're going to switch indefinite integrals to definite integrals. Okay, so first of all, we'll talk about a Riemann sum, named after some mathematician named Reimann, and to be honest, I don't know anything about him. Then we're going to talk about definite integrals. This is probably the single most important thing we're going to do in the chapter today. So today's lesson is pretty important. Then we're going to evaluate those, and then you're going to use some geometry to do all the calculus today. Okay, so Riemann sum. Let's talk about some notation first. Reimann came up with this weirdness. And so we'll break that down. Anybody know what the sigma stands for? By the way, that big capital E thing is a sigma. What's it mean, Mason?
It means the sum of...
Sum of whatever. It means add all these things up. So our notation is the following. Delta x is the width of the rectangle. We talked about that yesterday. How do you find delta x?
B minus A over N.
B minus A over N. Good. F of C sub I is the height of one particular rectangle. Any one, it doesn't matter, it's just some random rectangle. And then, of course, we said the sigma will add all those things up. So this notation should make sense with what we've already done. If we want to find the area under the curve, you find the area of a rectangle, find the area of another rectangle, find the area of another rectangle, and then when you're done, add all those up. So this is basically base times height for each rectangle, and then the sum, the sigma means now take all those and add them up. Okay? So nothing new there except the notation that represents those things. Are we good so far? Okay. So what Reimann said is he started doing the rectangle stuff that you did over the last couple days, and then he asked a simple question. Why do the rectangles have to be the same width? And the answer is they don't. And so he started to do this process again, but he changed the width of the rectangles. So if he may have 6 rectangles to add them up, they could all be the different widths. So that this became a series of rectangles where delta x changed from rectangle to rectangle. It sounds scary, but it's really easy. Okay, that's what's going to give us the Riemann sum. The Riemann sum is a sum of all those rectangles, most of which have different widths. Okay, so something like this. Now, why would you want to change the width of the rectangles? Well, because it might make the answer more accurate. It might, I mean, that doesn't look any more accurate than what we've done already, but it's just an example of what Reimann did, is that we don't have to have this constant delta x. So with Riemann sums, delta x is not found by doing b minus a over n. It's found by just choosing random values, which sounds a little wishy-washy, but we'll get there in a second. Okay. Now, what Reimann said is, I don't care how wide the rectangles are. I'm going to make them all different widths, but I'm going to introduce this thing called a partition, and the partition is denoted this way, with like double absolute value bars around delta. And he called that thing the norm of the partition. That's all fancy words. It just means look at all the rectangles, find the widest one, that becomes the norm now. Okay, pick the fattest rectangle out of all of them, and that becomes the norm.
So the norm is just the partition in the two lines?
Yeah, the partition are all the different widths of the rectangles, and the norm is the biggest, the widest one. Okay? And what Reimann said is what we've already talked about. I asked you a question when we first introduced this. I said, how do we get the area under the curve more accurate? And you told me
Smaller rectangles.
smaller rectangles or more rectangles. It's the same thing. So Reimann said, if I take the biggest, fattest rectangle and I take the limit as the width of that rectangle goes down to 0, I will get the most accurate answer possible. So that formula down in the bottom right-hand corner is actually Riemann's theorem. This we talked about already, the sigma notation we talked about already, and Reimann then said, if I take that fattest rectangle and I shrink its width down to 0, then I will have an infinite number of rectangles and the exact area under the curve. Notice the what is that thing? The symbol here changes from approximately to equals because that's the exact correct answer.
For the first equation we got, it was approximately.
Yeah, the stuff we've been doing already, they're all approximates. You mean this thing?
The one without the limit.
Yeah, that's just an approximate. This stuff, the sigma stuff, is just another way of writing what we've already done.
Okay.
Yeah, take all the rectangles, add them up, you get an approximate area under the curve. If you take the limit then of the fattest rectangle, then it'll give you an exact answer. And we're not going to be doing limits all over again. This is just the theory part of it. Does everybody understand the concept here? This is a fancy way of saying I'm going to take all the rectangles and shrink them down to a very, very skinny width. How skinny? 0. And if I have 0 width of rectangles, how many rectangles will I have? Infinite. So that's a sliding scale there. Either create an infinite number of rectangles or create rectangles that have 0 width. It's the same thing. That's not the practicality of it, that's just the theory. That transitions into something called a definite integral. A definite integral is an integral that will allow us to find the exact area under the curve. Everything we've done so far with integrals has been indefinite integrals where you take the integral and you get another function. Here we're not getting functions, we're getting numerical values. Okay, and the process is pretty easy. Okay, so this is in a color box, so it's probably going to be important. But what you need to write down, we don't care about this so much. This is the theory. Reimann said, well, if I shrink the rectangle, it's going to go down to 0, and that'll give me the exact area. Another way of doing that is this thing. And you've seen that before, except now I have an A and a B in there. The A and the B are called the limits of integration. It's the same A and B you've already seen. A is the starting point, B is the ending point. And we'll talk about how to find that later. I just want you to make sure you understand the notation. And then the terminology up there, lower limit is the same thing as the starting point, upper limit is the ending point. So we want to find the area under the curve from 0 to 4. A would be 0, B would be 4. Okay, so before we move on, is everybody understanding the theory here? Yes or no? Give me some feedback. Anything that's confusing? A little shaky?
Yes.
Okay. You're okay with a bunch of rectangles, right?
Yeah.
Okay, you've done that already. Are you okay with the concept of shrinking those rectangles to a width of 0? Okay, good. And as the limit of those widths go to 0, you get an exact area. Thank you.
Never mind.
Okay. Then we're going to talk about eventually how to do this. Today we're not going to do this. We're going to play with some geometry figures and make it real easy. And then a little bit more notation. Everybody good here?
Not yet.
Okay. Quick side note, remember, indefinite integrals give you functions. Definite integrals give you numerical values. It's an area. Kind of a 70s flare on those, the bottoms of those.
If you do the zipper. Like that.
No, but even without it, you got kind of a bell-bottom action going on there.
I didn't pick them, I just have to
Is
wear
that
them.
so you can slip them over your shoes?
We don't wear them for warm-ups.
But you could.
I
I mean,
guess.
they are warm-ups.
There are technically a travel suit, but
But when you travel somewhere, you have to then take off the travel suit because you're no longer traveling, right?
right, but I take off my shoes and put it on my basketball shoes.
Oh, you don't travel in your basketball shoes.
No.
Is that a big no-no? Is that like
We
volleyball?
only
You don't.
touch the court, yeah.
Oh, sorry. Danimal, same thing? You know, basketball shoes are just for the court, right?
During season.
sorry?
You like run when you walk outside.
Right. Like volleyball shoes. Yeah, the bottoms are too gummy.
Volleyball shoes are a thing.
Yeah.
Yeah. Volleyball shoes are more so
course.
than basketball shoes.
Ice skates
Probably not, but.
I'd say they're the same thing.
I'm not getting involved. Okay, here's some properties. The properties with integrals are very similar to properties we've seen with a bunch of different things. Okay. The integral of a sum is the sum of the integrals.
Oh, that makes sense.
The integral of a difference is the difference of the integrals. Okay, and again, this should sound familiar because we went through this exact process with derivatives. So I'm not going to spend a lot of time on it, I'm just going to go through it. You want to take the integral of something multiplied by a constant, move the constant out in front. Okay, so if I'm taking the integral of 8x squared, just take the integral of x squared and then multiply your answer by 8. This last one warrants some discussion. Why is the integral of f of x from a to a equal to 0?
Because delta x.
Eric.
Isn't the width 0 of the rectangle?
Right. The width of the rectangle is 0, therefore there's no area under the curve, so the value is equal to 0.
These look so intimidating
It's not.
because of the squigglies. Yeah.
The squiggly scare you?
Should we write down the squiggles?
It's up to you.
Because it's hard to write down sentences before you click it in.
Does it take you too much time to draw the squigglies?
Yeah.
And write the sentences.
I understand. Choose one or the other.
I'm
Do a
writing
different symbol if
sentences.
you'd like. I just wouldn't suggest you use that on the AP test. This kid used smiley faces for all his integrals.
If you got the right answer, like if you did that on the AP test, but you still were getting the right answers, how much points do you think they would take off?
Depends on the grading rubric.
Does it change every year?
It
Yep.
said 1 out of 1.
So when if you have a problem that's a definite integral, it depends on how they break up the points. They might give you points for the setup, they might give you points for the work, some problems just give you a point for the answer. They don't care how you got it, just give me the answer. So you'll see as we start to do more of those later. It's kind of wonky.
Sounds fun.
Okay, good? When you are setting up your definite integrals, a should always be smaller than b. And it would be nice if that were always the case. However, sometimes it'll be backwards. There's ways to fix that, which we're getting to in the next slide.
So you always have to manipulate it so that A is smaller than B?
I hesitate to use the term always, but you will frequently need to manipulate it so that a is less than b.
Okay.
So that the lower limit of integration is less than the upper limit of integration.
What is C?
Any number,
Oh.
a constant. Oh, and also notice when you take definite integrals, no plus c's anymore. Because we're not generating another function, we're getting a number. So to give an answer like 23 plus c doesn't make any sense. So don't do that. Okay. We can also split an integral into two different integrals. Now this is easy to understand if I draw you a picture. Okay, let's suppose I want to find the integral of this function from a to b. All right? We've learned now that this definite integral, this guy right here, represents the area under the curve. Is everybody with me? This is simple to understand if I just do this. Right?
Yes.
Yeah. A to C is the area of this region. C to B is the area of that region. And so just add the two puppies up and you get the integral that you're looking for. However, you need to be sure that C is between A and B, otherwise everything gets all kind of craziness. Why is that going to be helpful? Why would I ever do that? You probably wouldn't, but if you get to a point where you're looking for an integral over a to b and the functions change halfway through, so for instance, I've got a semicircle with a triangle, and this is a and this is b, you might want to throw a c in there, find the area of the semicircle, find the area of the triangle, add the two up, which is what we're going to be doing today. Okay. And then this fixes the problem I talked about. A should be smaller than B. If it's not, you just flip them. If you flip them, however, you've got to be sure to put that minus sign in front of it. This seems like a lot, but most of it will be almost second nature because it's things you've seen before, or they're things that are easy to manipulate. It's not that tough to stick a minus sign in front of it. There is, however, a concept that's going to wig a couple of you out. What's it?
The second part.
Second part.
It's just like.
It's saying that if you have a definite integral and the bigger or smaller values up on top or the bigger values on the bottom, if we're going from, let's say, 4 to 2, that's not good. So you can switch it the way it's supposed to be as long as you put a minus sign in front of it.
Okay.
Okay, so first example. We can do the math, this isn't that tough, but we're going to pretend we don't know these values. We don't know how to find the definite integral. Well, we actually don't know how to find the definite integral of x cubed. We can do it for x, which we'll get to in a bit, and we can do it for 1 dx. But they're going to give you this information. They're going to tell you what each of those things equals, and then they're going to ask you to find that. This is just purely a manipulation of the properties we just talked about. It's also similar to when we started doing derivatives. When we first started doing derivatives, we broke things down very simply. But we got to the point where we didn't need to do that anymore. This same thing is going to be true here. You're not going to need to go through the following process. You're just going to go and calculate that integral. But we're not quite there yet. So this we need to break it down a little bit. And it breaks down like the following. The integral of a sum or difference is the sum or difference of the integral. So I can start by rewriting it into 3 separate integrals. The other property we have is that if you have a function times a constant, take the integral of the function and then multiply by the constant. So I took all these constants, the 10, the 4, and the 3, and moved them out in front. Okay, so then I know what this is. That's right there. I know what this is. That's right there. And I know what that is. That's right there. Plugged and chugged. Got my answer. Is there anything disturbing about that answer? Luke?
It's negative, and it's supposed to be an area on the graph.
That bothers you?
Yeah, how do you have a negative area?
Right, it should bother you. This is a new concept now. So this is the thing that I was saying is going to bother a number of you. We're going to introduce the idea of a negative area, which makes no sense because in geometry and pre-calculus and everything else that you do, you always knew that if you did an area calculation, you got a negative answer, you screwed up somewhere. Now it's not a screw up. There's a legitimate answer for why we're getting a negative area. Okay, so the concept of negative area becomes a reality for us. And it's a simple explanation. Any area that ends up below the x-axis we now consider to be negative area. Okay, so this is what we've done already. We took some function, this happens to be the function of 2x, and we broke it into a bunch of rectangles. add up all the area of those rectangles, and you get the integral. But now what we're doing is we're saying, well, what if part of the graph is below the x-axis? This area down here is considered negative area. Okay. Let me say that again. Any area that ends up below the x-axis is considered negative area. So the answer to this problem in particular, well, let me ask you. Would the answer to this problem, if I found the integral from whatever this is, -2 to 1, would the answer be positive or negative?
Negative.
Why?
Because the negative area is bigger than the positive.
Good, then the negative area is bigger than the positive area, so when you add the two together, your final answer will be negative.
Can you go back really quick? Like that.
Oh, sorry,
Yeah,
misunderstood.
I
Yeah, I
think
got
it
you.
was-
One more?
No, the ones with the solutions.
These ones?
Yeah.
Okay. These ones? This one?
What are those? Oh my god. That was
Top where it
unexpected.
says give.
Did I miss something?
Those are
Do you know what are those?
highlight that.
You ever heard that before? No. It's like a media trend. Like for people.
Internet fad.
What are those?
What are those?
Don't explain it to him.
Okay, I understood it.
I don't
About
think it, I
shoes.
don't think it understands.
And not having up-to-date shoes.
Gotcha. You good? Okay. So, quick review. You should know those three things. Area of a triangle, 1/2 base times height. Area of a circle, pi r squared. Here's the one you may have forgotten, the area of a trapezoid. 1/2 h times b1 plus b2. Just so you know, the trapezoids we're going to be using are going to be lying on their sides. So what in geometry you would consider h will actually be delta x for us.
So should we just write down X?
You can write whatever you like. This is America.
PA.
Put the power right on.
But you would recommend which one?
Might be a good idea.
Okay.
H is delta X?
See. Okay, you ready?
No.
Here we go. Are you writing down the area of a circle?
I don't know if I should.
No, you shouldn't.
I'll walk it.
Okay, now we're done with the theory. Now we have the easy stuff. You ready? Let's find the area of that. Okay. In other words, we're looking for the area under the curve of the function 4 from 1 to 3. You with me?
Yes.
Good. Draw a picture of that first. Then we'll do the area.
Where does I get my iPad out?
Drawing pictures.
And you ask them for the homework.
Got it?
Apparently,
I don't understand what we're doing.
how do you draw a picture of that?
Can I just draw like a box?
Oh, come on. What's the graph of the function 4 look like? It's a horizontal line. So if we're looking for the area under a horizontal line from 1 to 3, what shape do you have?
A rectangle.
It's a rectangle. We'll get back to that in a second. How about that guy? Again, before we do the calculation, just draw a picture of that. The area under the curve x plus 2 from 0 to 3. And while you're doing that, if you can do that, you want to ask yourself, what shape am I working with here? And for you overachievers that are working above the normal curve, try that one. Don't look at me in that tone of voice. It is. What's the radius?
2.
Hey, Jen. Hey, Jen. Can I help you? You guys wanna,
Okay, so before we do any work, how tall is that rectangle? 4. How wide is it? 2. Therefore, the area is 8. And that's an exact answer. That's exactly the area under the curve. So the definite integral answer there should be 8 when we get done doing the calculation.
Can you repeat that?
Certainly. The rectangle has a height of 4.
Yes.
I'll have a picture for you in a second. It has a width of 2.
Okay.
You understand where the 2 came from?
Yes.
Where?
Sure.
I'm sorry? I knew that would get him. All right, here's the first one. It's a rectangle. The line, or the function y equals 4 is a horizontal line, so it would go on forever, but we only care from 1 to 3, which gives us this pink region, which is a rectangle. It has a height of 4, a width of 2. Done. What shape did you get in part B, or part 2? It's a trapezoid. Now, this is what I meant about h being delta x. Notice this is a trapezoid on its side. Base 1 is here, base 2 is here, and there's the height. How do I find this height? This one's easy because it's on the x-axis. How do I find that height? What's that? Excellent. Put the value into the function to find out where that point is. So there's base 1, 2. There's base 2, 5. There's the height, which is the same thing as delta x times a half. Gives you 21 halves. And again, that's an exact answer. What shape is the last one, Kaz?
Half circle.
Also known as a
Semicircle.
semicircle. Good. With a radius of 2. And we're looking for the limit of integration. Sorry, not the limit. We're looking for the definite integral from -2 to 2. In other words, find the area of that semicircle, which is the area of a circle divided by 2.
Can you go back to the first one for A?
Jen,
The rectangle?
sometime in the
Yeah.
basement we'll do table. Remember that?
Whoops. That one?
What's that?
Good?
Yeah.
Okay.
Maybe we could blow each other a little bit. Drink some spiky drinks.
Okay. Any problems?
Yes.
Just find the area of geometric shapes. But be warned, sometimes the geometric shapes will go geometric shakes. Sounds like a disease. You go to class, I get geometric shakes.
Shaking a perfect square.
Sometimes the area will be below the x-axis, so when that happens, you need to consider that a negative area.
Wait, we go back. Thank you.
When we get into actually cranking this stuff out, this thing of the absolute value pops up again, and you'll remember that it popped up when we were doing derivatives too, and we tried to avoid doing the derivative of the absolute value because it was nasty. The same is true with doing definite integrals. We don't really want to find the definite integral of the absolute value of x, but what we can do is think about it graphically. The absolute value of x is that V shape, and if we're looking for the absolute value of the integral of the absolute value, we want the area under the curve. So you see, going from -3 to 2, I just split it into 2 triangles, a purple one and a brown one. Just find the area of each of those triangles, add them up, and you get your answer there. The tricky part is going to be finding these distances, but as Ryan said, if I want to know how tall that is, just put -3 into the function. So absolute value -3 is 3. That's got to have a height of 3. It's got a width of 3. This one, how tall is it at 2? Put 2 into the function. The absolute value 2 is 2, so it's 2 by 2. So 3 times 3 divided by 2, 2 times 2 divided by 2 gives you 4.5 plus 2, 6.5. Okay? We will continue to come back to the same statement, and that statement is the definite integral is the area under the curve. How are you going to find that area? And today's stuff is pretty much just geometry. Find the area of shapes. Are we solid? Awesome.
Could you
Question?
go back one side, please?
Sure.
Literally, so much chemistry, like,